everyone, welcome back to my YouTube channel of subject Basic Electrical Engineering. Myself Pankaj Shah, and previously we have started one chapter, that is DC circuit. In this chapter, we have seen some network theorems, and that network theorems are Thevenin's theorem, Norton's theorem, and Superposition theorem. We have studied the steps to apply Thevenin's theorem to any kind of electric circuit. And in today's video, you are going to study about a Norton's theorem and a superposition theorem. This two theorem again is applicable to electric network, but this two theorem is somewhat different than Thevenin's theorem, and it makes our electric network analysis very easy. So now let's see what is Norton's theorem. So basically Norton is dual of Thevenin's theorem. If you have studied, if you have seen the videos related to Thevenin's theorem, then you can easily understand Norton's theorem because it is just similar to Thevenin's theorem. But there is somewhat change of steps in this Norton's theorem. So let's see first the statement of Norton's theorem. So Norton's theorem states that in any linear bilateral network with two output terminals can be replaced by, means if you want to find current or voltage through any branch in any linear bilateral network, then you have to replace the whole network except the load resistance branch. So you have to replace the whole network by a simple equivalent Norton's current source IN and a resistance, equivalent resistance in parallel with that Norton's current source. So in Thevenin's theorem, we were replacing whole network by a voltage source and a resistance in series with it. And in Norton's theorem, similarly, we are replacing the whole network except the load resistance branch, but by a simple equivalent current source and a resistance in parallel to it. So IN will be the value of that current source, Norton's current source, and RN is the equivalent Norton's resistance. So let's see the network which is previously given. So in this network, the all other branches are given. Whole network is there, and this is the load resistance branch through which we want to find the current or a voltage. So you have to replace this network by this network. And this network is nothing but the Norton's equivalent network. So you can see here, there is a current source which is nothing but the short circuit current flowing through this load resistance branch. We will discuss later on how you can find the value of this current source. And this is nothing but the Norton's equivalent. And these are the branch A. And after finding this Norton's current and Norton's resistance, we will connect our load resistance branch back to this terminal A. So this is our load resistance branch. So we have to temporarily remove this load resistance branch. And lastly, we will bring this branch back to the terminal as it is. In the previous figure, ISC is nothing but the current flowing through the load resistance branch, but we have to remove the load resistance branch and we have to short circuit the terminals A and B. We have to remove this load resistance and we have to short circuit this terminal A and B. So if we short circuit this terminal A and B and the current, if we find the current flowing through that short circuit branch, then it is known as the ISC, that is short circuit current. And this ISC is nothing but the Norton's current, value of the Norton's current source, RN. So this RN is nothing but the Norton's equivalent resistance. And this is just similar to, this step is just similar that we have used in Thevenin's theorem. So that means you have to remove all the sources from the given network and you have to open the terminals A and B and you have to find the equivalent resistance as seen from the AB terminal. So it will be the same step as we have seen in the previous Thevenin's video. But just name is changed. In previous video, we were using RTH and here we are using RN. Also, you can use RTH here because the steps are. So now let's consider this example. So look at carefully what we want to find is determine current flowing through RL using Norton's theorem. Here it is mentioned that if it is not mentioned, you can either use Thevenin's theorem, Norton's theorem, or superposition. So here we need to find the current flowing through this load resistance branch. So it is named as A and B branch, or A terminal and B terminal. So step number one, temporarily remove the load resistance branch. So temporarily we have to remove this load resistance branch. And previously in Thevenin's theorem, we were finding open circuit voltage across that open circuit terminal. But here we need to find the short circuit current. So if you want to find the short circuit current, then what you have to do is you have to short circuit the terminals. So we have removed this branch and we have short circuit this AB terminal. You can look at here, AB terminal is short circuit. So now our aim is to find the short circuit current flowing through this AB branch. So how we can find the short circuit current? So here you can see that you have to find the equivalent resistance. And equivalent resistance can be obtained from opposite end to the source. So source is connected here. So you can find the equivalent resistance of this network particularly can be obtained by here. So here R3 is connected and R3 is in parallel with R2. And this parallel combination is connected in series with R2. So you can say that R1 is in series with the parallel combination of R2 and R3. So R2 and R3 can be solved as product by sum. So it will be R2 R3 upon R2 plus R3, and this combination is in series with R1. So this is equivalent resistance of particularly this circuit. Why we have obtained equivalent resistance? Because if you want to find the current flowing through this source, the total current flowing through this source, then you have to find the total resistance. So we have obtained the total resistance. So now let's find the current flowing through this source. So the current drawn from this source is obtained by I is equals to V by R, where V is the value of this voltage source as E and R is the equivalent resistance of this circuit that we have obtained. So let's put the value of V and R in this equation, then it will be I is equals to E upon equivalent resistance R. Now, if you want to find the current flowing through particularly this branch, then you have to use the current divider rule, because I is the total current drawn from this source. So this current is here. Now this total current is flowing into two parts. It is dividing into two parts. One part of this current is flowing into this resistance R2, and another part of that current is flowing into this branch, that is R3 resistance branch, and also this branch is nothing but the short circuit branch. So in current divider rule, what current divider rule's formula is? ISC is equals to, first you have to put the value of the total current, that is I, into. If you want to find the current flowing through this branch, then in numerator you have to write down the value of opposite branch resistance. And opposite branch resistance is R2. So you will place R2 here and divide it by addition of both branch resistance. So here the resistance value is R2 and here the resistance value is R3, because this is a short circuited path, so resistance is 0. So it will be R2 plus R. So in this way you can find the current flowing through this short circuit branch. So this was all about the Norton's current value. Now let's talk about the Norton's resistance, or you can say Thevenin's resistance, because both steps are same. So remember that to find the Thevenin's or the Norton's resistance, we have to remove all the sources connected in that given diagram. So in given diagram there was a voltage source. So we have to remove that voltage source by a short circuit branch. So we have short circuited that voltage source. So now in the diagram we have three resistances. One resistance is R1 here, another resistance R2 is here, and another resistance R3 is here. And you have to find the equivalent resistance from this network as seen from terminal AB. So if you want to find the resistance as seen from terminal AB, then you have to solve this equivalent resistance from the opposite side. So if you solve this from the opposite side, then you can clearly see that this R1 and R2 is in parallel because it is connected at this node. So these two are in parallel, and the answer of this parallel will be in series with this resistance. So you can say that R1 and R2 is in parallel and their answer will be in series with R3. So this parallel combination can be obtained by product by sum, that is R1 into R2 upon R1 plus R2 plus R. So this is nothing but the Norton's resistance. So now step number 4. So in step number 4, you have to replace the entire network except the load resistance branch by Norton's equivalent network. So Norton's equivalent network is like this. Here we have to replace a current source which value we have already obtained. So it is IN, and you have to put one resistance in parallel to it, that is RN. So it is IN R. Now step number 5. You have to connect the previously removed branch back to the terminal A. So previously we have removed the load resistance RL, and now we have to connect that load resistance branch back to this network. So this is final Norton's equivalent network. There is one current source ISC or IN, there is one resistance, that is RN or RTL, and there is a load resistance. And our aim is to find the current flowing through this load resistance. So if you want to find current flowing through this load resistance branch, then already we have a total current ISC. And this total current ISC is distributed into two parts. So again, we have to use the current divider formula. If you want to find the current flowing through this branch, then IL is equals to, first of all, total current, that is ISC, into, if you want to find the current flowing through this branch, then in numerator it will be opposite resistance. So that means it is RN divided by RN plus R. So this is the final answer of the load current flowing through our load branch by using Norton's theorem. Let's consider one numerical based on this Norton's theorem. So we have taken one network here just similar to the previous theoretical network, but here we have taken some values. So what will be the first step? First step is you have to remove the load resistance branch, that is 5 ohm, and you have to short circuit this 5 ohm branch. So we have removed this 5 ohm resistance and we have short circuited this branch, and we need to find the short circuit current flowing through this branch. So what you have to do is you have to apply the total resistance formula. So how you can find the total resistance? So this 5 ohm and this 10 ohm is in parallel. So their answer will be in series with this 10 ohm. So 5 and 10 is in parallel and their answer is in series with this 10 ohm resistance. So 5 ohm and 10 ohm in parallel can be resolved like product by sum. So it will be 10 into 5 upon 10 plus 5. So 10 ohm will be in series. So if you solve these values, then you get 13.33 is the equivalent resistance of particular this network. Now if you want to find the current drawn by the source, that is the total current I, then you have to do V by R. V is nothing but the 120 volt and R is the equivalent resistance of this resistor. It is 13.33, and if you do this in calculator, then it will give you 9 ampere current which is drawn from this source. But our aim is not to find this current. Our aim is to find the current flowing through this short circuited branch. So you have to apply the current divider. Current divider rule states that if you want to find the current flowing through this branch, then ISC is equals to the total current I, that is 9, into the opposite resistance, that is 10, upon the total resistance, and total resistance of this network is 5. So 10 plus 5. So 10 upon 10 plus 5. So it will give you 90 upon 50. 90 upon 50. So this 90 upon 50 gives you 6 ampere. So the short circuit current is nothing but the 6 ampere. So we have obtained the Norton's current. Now next step is we have to find the Norton's equivalent resistance. So to find the Norton's equivalent resistance, you have to remove all the sources from that network. So we have short circuited the 120 volt source. So now we have 3 resistances here, and we need to find the equivalent resistance as seen from this terminal. So we have to solve the resistance from the opposite side to this. So opposite side is this. So this 2 resistance is in parallel. So 10 ohm and 10 ohm is in parallel, and their answer will be in series with this 5 ohm. So 10 is in parallel with 10, and their answer is in series with this 5. So 10 and 10 in parallel can be solved by product by sum, 10 into 10 upon 10 plus 10 plus 5, and the answer will be 5 ohm. So we obtain the Norton's equivalent resistance as 5 ohm. Now what we have to do is we have to draw the Norton's equivalent network. So the Norton's equivalent network is nothing but the short circuit current ISC, that is 6 ampere. Norton's equivalent resistance in parallel to that current source, which is 10 ohm, and load resistance connected back to the terminal A. So this is nothing but the Norton's current. Now our aim is to find the current flowing through this 5 ohm branch. So if you want to find the current flowing through this 5 ohm branch, then you have to apply the current divider rule. That is the total current, that is ISC 6 ampere, into If you want to find the current flowing through this branch, then opposite will be in numerator. So 10 ohm will be in numerator and addition of these two resistances will be in denominator, that is 10 plus 5. So it will be 60 upon 50. So this 60 upon 15 will give you 4 ampere. So 4 ampere is nothing but the current flowing through our required branch. So in this way, in any network, you can find the current or voltage by using Nortons theorem. Now let's see the superposition theorem. So in superposition theorem, it is used to solve electric circuit which have more than one energy source. Previously, in both the theorems, in Thevenin's and Norton's theorem, there was only single voltage source. But if there are so many voltage source or a current source given in any network, then you can use this superposition. It is applicable only to linear circuit. Thevenin and Norton also applicable to the linear circuit. Therefore, it is not applicable to circuit which have non-linear elements like diode, transistor, etc. So now let's see the statement of superposition. So in any linear bilateral network containing more than one energy source, then the resultant EMF, or you can say current flowing in any element. If you want to find the current or a voltage in any element, then it can be obtained by considering each source separately. Means if two sources are given, then you not have to consider both sources at a time. You have to consider first source alone and then you have to consider second source alone. Then considering the sources separately, while all other sources should be replaced by their internal resistance, and then algebraically adding that separate response, that is separate voltages or separate currents, you can find the total voltage or current flowing through your required. So this is the statement of superposition. Now let's see, if we are considering this simple network, find out the current flowing through this 9 ohm resistance. If you want to find the current flowing through this 9 ohm resistance, then how you can apply this superposition? Here two sources are given. One is the voltage source and another one is a current source. So first, if we consider only this voltage source, that is 3-volt voltage source. So you have to remove this current source and you have to replace it by its internal resistance. But here no internal resistance is given, so this current source will be only open circuit. So we have open circuited this current source. So now we have only this network. Our aim is to find the current flowing through this 9 ohm branch. So in this case, let's say that current flowing through this branch is I9 dash, because this is a separate response obtained by this only 3-volt source. So if you want to find the current flowing through this branch, then you have to apply the Ohm's law. So I is equals to V by R. Here V is nothing but the 3-volt and R is nothing but the 6 plus 9, because both are in series. So 3 upon 6 plus 9 will give you 3 upon 50 and will give you 0.2 ampere, and the direction of current will be positive terminal, that means A to B. So direction is important, A to B. If in second case current is flowing in B to A, then you have to subtract the individual response. If both are from A to B, then you have to add the response. Okay, so now step number 2. Let's consider the 2 ampere source alone. So if we consider this 2 ampere source alone, then this 9 ohm branch will be as it is, the 6 ohm branch will be as it is, but this source, that was the voltage source, is now replaced by its internal resistance. But again, no internal resistance is given, so it is only short circuit. So we have short circuited that 3-volt source. Now our aim is to find the current flowing through this 9 ohm branch. Now this current I is flowing in this direction, so this current will be distributed into two parts, that is 6 ohm and 9 ohm, and this current will flow in the same direction, A to B, and let's say that this is I9 dash. So to find the current flowing through this 9 ohm branch, you have to use the current divider rule. So current divider rule states that first of all put the total current, that is 2, into the opposite resistance, that is 6, upon total resistance, that is 6 plus 9. So it will be 12 upon 50. So it will gives you 0.8 ampere, and this is from A to B again. So in both the cases we obtain the current and the direction of that current. So now to find the total current flowing through this 9 ohm resistance, you have to add both individual response obtained by the individual sources. So first was the I9 dash, second one was the I9 double dash. So if you add these two results, you get the total current flowing through that branch with both the sources. So it will be zero point 0.2 plus 0.8. So it will be 1 ampere. So this is nothing but the superposition. Let's take another example. In this example, we need to find current through all resistances, not particular resistance. We need to find the current through all resistances. And by using superposition theorem, you can clearly see that there are two voltage sources. One is the 50-volt source and another one is the 25-volt source. So what you have to do is step 1, consider 50-volt source alone and replace the 25-volt source by short circuit because no internal resistance is given. So if we are replacing this voltage source, then network will be like this. Now, if you want to find the total current, all branch current, then first of all you have to find the current drawn by this source, and that current is nothing but the I1 dash. That is the total current, and that total current will be distributed into two parts. That is I2 dash and I3 dash. So basically, first of all, you need to find the total current. To find the total current, you have to calculate the total resistance. So the total resistance will be this 5 and 30 will be in parallel and their answer will be in series with this 10. So it will be 10 plus 3 and 5 is in parallel. So it will be 3 into 5 upon 3 plus 5 and their answer will be added to this 10 ohm resistance. So which will give you 11.9 ohm. So you got the total resistance of this network. Now if you want to find the current drawn by this 50-volt source, then it will be I is equals to V by R. V is 50 and total resistance is 11.9. So you got the answer of current flowing through this 10 ohm resistance as 4.2 ampere, and this is the total current I1 dash. Now this total current is distributed into two parts. So by using current divider formula, you can find the current flowing through these two resistances. So if you want to find I2 dash current flowing through this 3 ohm branch, then what you do is total current, that is 4.2, into opposite resistance, that is 5, upon total resistance, that is 5 plus 3. So you got the answer 2.63 ampere. If you want to find the current flowing through this 5 ohm resistance, then the formula will be again same, that is the total current 4.2 into, if you want to find the current flowing through this branch, that opposite resistance is 3 upon the total resistance, that is 3 plus 5. So you got the answer 1.58. So in this case, we have obtained current flowing through each resistor as I1, I2 and I. I1 is flowing in this direction, left to right. I2 dash is flowing from A to B, and this 5 ohm resistance is also left to right. Now let's see the another source along, that is 25 volt. If you are considering 25 volt source alone, then you have to short circuit this branch. So we have short circuited that 50 volt source. Now we have to calculate the current flowing through this 25 volt source. So that is the total current and it will be I3 double dash. And this I3 double dash is distributed into two parts, that is I2 double dash and I1 double dash. So if you want to find the total current drawn from this source, then you have to calculate the total resistance. And again, you have to calculate from the opposite side. So it will be 10 and 3 is in parallel and this 5 is in series. So it will be 5 plus 10 is in parallel with 3. So this 10 in parallel with 3 will give you 10 into 3 upon 10 plus 3. And this 5 ohm is in series. So if you solve this, and it will give you 7.31 is the total resistance of this whole network. Now if you want to find the total current drawn from this source, then it will be V by R. V is nothing but the 25 volt and resistance we have obtained here is 7.31. So it will be 25 upon 7.31, which gives you 3.42 ampere. This is the current drawn from this source, and this current is nothing but the 5 ohm current, that is I3 double dash. Now this current is having the opposite direction, so we will subtract from the previous one because both are in the opposite direction. Now this total current is distributed into two parts, so by applying current divider you can find the current flowing through this both branch. If you want to find the current flowing through this 3 ohm branch, that is I2 double dash, then first you have to put the total current, that is 3.42, into opposite resistance, that is 10 upon 10 plus 3, that is 13. So you get the answer as 2.63 ampere. If you want to find the current flowing through this 10 ohm branch, then it will be total current 3.42 into opposite resistance, that is 3 upon total resistance, that is 10 plus 3. So it will be 30. So the solution of this gives you 0.78. But again, this and this current is in opposite direction, because in previous case current was flowing from left to right. Here in this both branch current is flowing from right to left. So you have to subtract the results. And in this branch current previously was flowing from A to B, and here also it is flowing from A to B, so it will be I. So now let's calculate the total current I1, I2 and I3. So current in 10 ohm resistance will be subtracted. The subtraction will be from larger value to the smaller value. So I1 dash minus I1 double dash. So it will be 3.40. In the third branch, it is also it is added, because current is flowing from A to B, so it is added like this 5.26. And in the third branch, the current should be subtracted, so it will be 3.42 minus 1.58. It is 1.80. So in this manner, we can calculate the current or the voltage through any branch by using superposition theorem if more than one source is given in that. So this was all about the superposition and Nortons theorem. Thanks for watching this video. Stay tuned.